is the archetype of the first-person shooter genre and helped define an entire generation of games in the 1990s. While not the first of its kind, nor even the first by developers id Software, it was a game that changed the landscape of the industry. And it's an important topic to explore, not just because of its popularity, but because, much like other games from the 90s we've explored on this channel, it achieved so much using limited hardware and without many of the tools and standards game developers and players now take for granted. Doom is, in essence, a dungeon crawler with guns, in which players must navigate a myriad of complex non-linear environments to find keys and activate switches that will move you one step closer to the exit. Along the way, players fight hellish and demonic creatures, ranging from possessed gun-wielding soldiers to fireball-tossing imps, flying enemies such as the Cacodemon in Lost Souls, and the brute strength of the Pinky and Baron of Hell, with the sequel Doom 2 Hell on Earth, released in 1994, adding even more variation, with Hell Knights, Revenants, Arachnotrons, the Mancubus, Pain Elementals, and the Archvile. All of these characters move through the world, respond to player behaviour, and attack using their own internal logic. Perhaps the most impressive aspect is the sheer number of enemies that the game can accommodate at once, all the while handling movement, line of sight tests, collision checks, interactions, and more. But Doom was no slouch. The game capitalised on the huge changes happening in the home PC market of the period. Hardware was becoming more affordable, and the landscape had shifted in a way that benefited game development. Intel CPUs, notably the 486 from 1989, was becoming increasingly affordable, with the 486DX2, released in 1992, proving even more powerful. RAM was becoming cheaper, and the move towards Windows 3.1 had pushed towards graphics adapters and chipsets becoming more commonplace. This change in the market led to id Software throwing out pretty much everything they'd built for their previous game, Wolfenstein 3D, in 1992, and as we'll see, there are numerous optimizations to the code that allows for it to achieve things that similar games of the era would fail to replicate. Doom's enemy AI is but one class of object in the game known as a thinker. These are any object in the game that has to make a decision that typically will process or evolve over a period of multiple frames. The original DOS build of the game runs at 35 frames per second, with each frame handling the logic for all four main classes of thinker. The first class is all of the actors, meaning the player, non-player characters, and the level itself. Secondly, there's the status bar on the bottom of the screen, then the in-game map, and lastly, the rendering of the HUD itself. The actual core logic of the enemies is a finite state machine, a simple but effective mechanism to state that a character executes a specific behaviour when in a given state, and what the conditions are that will force it to change. As discussed back in my AI 101 episode on finite state machines, Valve's Half-Life popularised FSMs for modern shooters, courtesy of the nature of its C++ codebase, while also providing mechanisms for characters to have goals they can try to satisfy. Plus, it's worth mentioning that even to this day, finite state machines are still adopted, not just in the likes of popular franchises such as The Last of Us, but also actually in the modern reboot of the Doom franchise. Doom operates in a similar structure to Half-Life, but it lacks a lot of flourishes that would later appear in games such as GoldenEye 007, and of course Valve's ever-popular shooter, but also some of the more seamless integration. The big reason for this is that there's no scripting language in the Doom engine that allows for designers to configure the NPCs to do what they want. As we'll see shortly, the actual logic is all written in the C programming language, and there's a lot of very clever tweaks implemented to allow for the variety of different enemy designs, not to mention all the encounters players face in the game. The full diagram of the state machine is shown on screen now, and there's some interesting quirks in how it all works. So let's discuss the high-level behaviour, and then I will burrow down into individual topics. Enemies always start in the spawn state, a mechanism whereby they are idle and await an event that will force them to go into a more active behaviour. They're waiting to see or hear something that will force them to act, and will simply walk on the spot until then, though sometimes a designer can override it. Players of Doom will have spotted this on occasion, though the most obvious instance is in Entryway, the opening level of Doom 2, where the zombie-men have their back to you. In fact, this happens a lot in the opening levels of Doom 2. Never really thought about that until now. Upon receiving a sensory input to tell them the enemy is nearby, they go into the C state. which allows them to move around the map and head towards their designated target. We'll go into more detail shortly on how all of that works. Provided the situation will allow it, an enemy can then attempt to attack the player, resulting in them moving into the melee or range states, reverting back to the C state once the attack is complete. Meanwhile, the monster can only enter the pain state externally, which makes sense given it should only happen when the player hurts it. Otherwise, that would mean the enemies are essentially hurting themselves, I guess. It then plays the corresponding frames for rendering, any sound effects, and then gets back to core logic. As we'll see in a second, NPCs don't go into the pain state every time they take damage, but instead it's based on a probability that is encoded in the enemy's design. Lastly, a monster can die in one of two ways. There is the simple die state, brought on by the monster receiving a total amount of damage that exceeds its starting health. However, there's a special case called X-die, which is used for when a monster is gibbed and turns into a pile of goop. Once again, these states can only be transitioned into by external logic, rather than the monster itself deciding it should turn into freaking confetti. The gib will only occur if the damage received at the time of death exceeds the remaining health of the monster plus its original starting health. So, for example, imps start with 60 health points. If it's been shot already and it's down to 10 health, then in order to be gibbed, it has to receive a minimum of 71 damage on the next attack. Given the lower starting health values of the likes of the zombieman and shotgun guy who have 20 and 30 starting health respectively, it's relatively easy to gib them with an exploding barrel, the rocket launcher, or even the berserk pack. Meanwhile, enemies such as the Cacodemon or Hell Knight, which have 400 and 500 health on start, are practically impossible to gib. That said, you can gib pretty much any monster if you telefrag them, meaning you teleport into them, given that does 10,000 damage. Great example of this is in Perfect Hatred, the second mission of Doom's Thy Flesh Consumed episode, where you can telefrag the Cyberdemon, given it only has a meager 4,000 health. You'll notice there's one last state, Raise. This was introduced in Doom 2, courtesy of the Archvile, the demonic priest that can resurrect all enemies with exception of the Lost Souls, the Cyberdemon, the Spider Mastermind, and other Archviles. As we'll see in a minute, this actually results in some weird behaviour during its actual execution. So let's get into that next. Each enemy adheres to the state machine, but their individual behaviours are quite distinct. So how are they defined and how do they work? To execute the logic, any actor such as an enemy is spawned in with a thinker object attached to them. Each thinker is a struct written in the C programming language that has inside it a pointer to a function of game logic the enemy must execute, alongside a range of additional variables that help it take shape. This function helps each monster to determine the particular behaviour they should exhibit based on its current state. But the actual definition of each enemy in Doom is achieved outside of the codebase. A text file from the project is imported and compiled into an info file, which contains within it all of the enemy's specification as well as the definitions for all of the states for each individual character. So let's check out two examples from the codebase. On the left is MT_troop, the internal name for the imp, and the right is MT_shot guy, which is the sergeant, or, shotgun guy. The information from the text file is compiled into a struct that carries the following elements: their internal ID number in the game, the amount of health the character starts with, their movement speed, the probability of pain state interrupts, their radius and height, and the specific properties of the NPC in context of the engine. In this case, imps are solid objects you can't walk through, they can be shot and damaged, and their death counts towards the total number of enemies in the level. Now let's pause for a second and wind this video back a couple of minutes to when I talked about the pain state. At that time, I mentioned that the monster doesn't always go into the pain state when hurt. Instead, it is influenced by the pain state interrupt probability, which in the codebase is referred to as pain chance. Every time an enemy is hurt by a weapon, there is a probability check to decide whether the enemy will go into the pain state, thereby interrupting its movement and any attacks. The number ranges from 0 to 256 and is configured for each enemy type. So in the case of the imp and shotgun guy, these are 200 and 178 respectively, meaning that the imp, anytime it is hurt, has a 79.3% chance of being put in the pain state, while the shotgun guy only has a 67.6% chance. But the trick is that each individual hit from a weapon counts towards this. So while a rocket counts as only one hit, the shotgun technically has 7 separate attacks courtesy of its spread. This is why the minigun is such a useful weapon against the likes of the Cacodemon and Arachnotron, because each monster has a pain chance of 128 or 50%, but each consecutive bullet fired is another opportunity to trigger the pain state, or, as it was referred to in the original Doom manual, making them do the chain gun cha-cha. This has a huge impact on weapon selection during gameplay, to a point that it's so intrinsic to the gunplay of Doom that it was re-implemented in the 2016 reboot. Some enemies have incredibly low pain chances, with the Cyberdemon and Archvile both in single digits, while others, like the Lost Souls, have a 100% pain chance. Also, technically, the barrels have a pain chance, but it's set to 0, which, makes sense because they're barrels. Okay, so let's get back to the definitions. On top of all the information about the behaviour of the enemy itself, we can also see each of the individual action definitions. These are custom definitions for each of the states in the state machine, so we can see that the imp uses the attack action for both the melee and ranged FSM states. Meanwhile, the shotgun guy doesn't have a state defined for melee attacks. Now, as for the actions themselves, these are actually a lot more complicated. Each state is compiled into a definition for each individual action frame that is executed in that state. So if we consider the attack for the imp, it blows up into even more information. This includes the family of sprites that are read from when rendering this behaviour, and the frames to be used from that sprite set, the number of in-game ticks that the frame executes for, the in-game action in the source code that should execute on that action frame, and the next action frame it should then execute. So in the case of the imp attacking, it will render the first 2 sprites for 8 frames each, and run the code that ensures the imp turns to face the player, then draw the 3rd sprite for 6 frames and run the special troop attack function, which is designed specifically for the imp. Once it has finished the 3rd action frame, it will then transition back to the main C state for the imp. And when you look at the code for troop attack, it highlights why there isn't a separate state for melee versus ranged attacks, given the imp will check if it's in melee range and then commit to that, or it will simply launch a missile at the player. These rules are in place for things such as enemy characters attacking the player, dying or being gibbed after taking damage, plus things like animated sprites in the environment. The fun part is returning back to the raise state mentioned earlier. Any enemy that can be resurrected by the Archvile has a set of raise action definitions, which have the exact same set of sprites used for dying, but it plays them in reverse. One last thing is that for each of these action definitions, we need a separate frame of animation, but that hides a further complexity, given enemies in Doom can be rendered from 8 different angles relative to the player's position. So when one of these sprite families is being used, it always pulls the appropriate set of sprites for this character based on their angle relative to the player. So in the case of the imp, there are 21 unique sprite indices, meaning you have 168 individual sprites to cover all 8 angles. However, one optimization to this is that some characters, such as the imp, are symmetrical, so instead of having 8 sets of sprites, there's only 5, and if a sprite set for that orientation is missing, it simply takes the mirror equivalent. This reduces the imp sprite set from 168 to 105. Sadly, some characters such as the Cyberdemon are not symmetrical, and so they still have to build each individual sprite. Now that we know the overall core logic for the enemies in Doom, next up I want to focus on the C state, which is when an enemy has found a target and then locks in on it, chasing them around the map and attacking when they can. As mentioned already, the spawn state has the enemy standing around and waiting for something to trigger them. This can happen in one of 2 ways. Either they see an enemy or they hear them. In either case, it establishes a target for the NPC to head towards. There are some extra checks here as to whether the target is shootable, meaning they don't become skittish and hunt down anything that makes a noise, but also there's... No, you know what, I'll tell you the other secret in a minute. Once the target is established, it moves into the main C state from the diagram. This corresponds to a chase function in the codebase, whereby the enemy will begin to hunt, and if it's within range for a melee or ranged attack, it will take the shot. But wait a minute, let's back up. how do the enemies even see you? This is actually a huge chunk of logic for Doom, given it's tied to how the maps are designed. Plus, it's also one of the most interesting aspects of how the game is optimized. In previous videos on games such as The Last of Us, Splinter Cell, and Alien Isolation, we talked about how vision cones are used for enemy sight. Doom predates all that stuff, but also it's designed for early 90s PCs, and quite often there are dozens of enemies running sight checks at once. Even if all the enemies are in the spawn state, then each of them are calling the look function in the codebase 35 times a second. So not only does it need to work effectively, it also needs to be optimized. Doom enemies technically have 180 degrees of vision, and have no long distance vision cutoff. If the view between yourself and the enemy is not obscured, they will see you. Plus, height differential doesn't matter. That's because Doom is a 3D render projected from a two-dimensional floor plan. The line of sight is parallel with the floor, hence you'll notice that if you're above or below an enemy, if it's facing you then it will always notice you, even if sometimes you can't see them in return. So how does it ensure that an enemy can see you within its field of view and also navigate towards you in a way that's cost effective? The trick here is that Doom's map is broken up into chunks using what are known as sectors, and these sectors are organised courtesy of a binary space partitioning algorithm, or BSP. A BSP allows you to organise objects such that they retain spatial information. This is used so the game's renderer always knows what parts of the map it needs to draw by only rendering the current sector and any connecting sectors according to the BSP, and it draws them in the right order. This optimization was added by programmer John Carmack to cut down rendering costs, given it saves on performance by ensuring it doesn't try to render the entire level, an issue that modern game engines have now rectified. Now from this, some further optimizations can be made to the AI as well. The map being broken up into sectors means that, much like the BSP, you can record information about whether it's possible for one character to see another based on their location. Visibility between sectors is actually pre-computed in Doom courtesy of what is known as the reject table. This tells us that if a character is in a given sector, whether they could even potentially see another character in another sector. So in this example here, it's practically impossible for the character in Sector A to see anyone in Sectors C and D, but it could in theory see you in Sector B. So when you're looking for the player, the game quickly does a check against the reject table to see whether it should even bother running the sight test. Note that this only works for vision. We'll come back to sound in a minute. Once the player has been seen and a target is acquired, then the monster will start moving towards you. Technically, there isn't any actual pathfinding in Doom. If there's a direct path towards the player, then it simply moves towards you. If there isn't, then it tries to head in that direction and will bounce off walls changing direction as it goes. In the event there's no possible direct path to you, then it will move around randomly instead. In order to manage all of the enemies and the player colliding with the level, all of the collision data is pre-computed as well. The block map breaks up the map of the level into a grid that allows it to quickly check if any space in the world is navigable. So yeah, if an enemy sees you, it's going to kick off and the situation will get a little tense. But what about when you pop into a room, fire off the shotgun, and everything roars in anger at you? Well, here's the funny thing. Yes, the enemies in Doom can hear you, but not in the way you would think. I mean, one could argue that the enemies actually see sound. I mean, it literally sets a sound target in the look function after all. When the player fires their weapon, it sets the player as a sound target in the sector of the map that the player is standing in. If an enemy is in a sector where a sound target is created, it will wake it up and hunt the sound target when it runs the look function. But that would only work in one sector unless the sound could travel. Doom actually has very simple sound propagation, whereby a flood fill algorithm spreads the sound around the map within a certain range, provided there are no blockers that prevent the sound dissipating further. A good example of this is in Deimos Lab, given the entrance opens out to a long corridor at the left hand side. As soon as you finish fighting the imps and shotgun guys at the entrance, you'll soon be attacked by imps who heard all the commotion hundreds of meters away, given the gunfire propagated through the space. Doors between level chunks will block the sound travelling further, but also level designers could place blockers where they wanted to make sure the sound didn't travel into areas where an ambush was being prepared. One of the most memorable aspects of Doom is that the monsters have a habit of infighting. They'll tear chunks out of each other if the mood strikes them. How on earth does that even work? Well, it's actually quite simple. There's logic in the code that states in the event an NPC is attacked and hurt by another character, then it will assign that character as their new target, even if it's not the player. Naturally, this means that the demons don't attack one another without cause, so you need to lure one enemy into the line of fire of another and hope it accidentally causes some friendly fire. There are some exceptions to this. Given Barons of Hell and Hell Knights can't hurt each other with their attacks, Pain Elementals technically can't get caught in infighting because they hurt other characters by spewing lost souls, which will then get targeted instead. And there's a specific edge case in the game code to stop Archviles being attacked by other NPCs, which means you need to go and smash that bastard's skull in yourself. Typical. We've explained the core logic, how individual state actions are defined, and the optimizations for pathfinding, visibility, and sound checks. But that isn't enough to make Doom behave the way it works. The game is full of traps, of dead ends, and much more that helps create these rich and interesting encounters. The trick to this is two critical parts of the codebase that help influence the game's design. First of all, the game has a variety of different custom actions that can be synced up with the map. If you've ever cracked open a Doom map, you'll have noticed a lot of lines that hide inside it. Some of this is the actual geometry, while others are essentially trigger volumes, meaning the game can detect when the player crosses into that volume. It's a very common practice in modern game engines. One trick Doom heavily employs is the level editor allows for code snippets to be executed upon entering a volume, and it can also add a tag that references what parts of the map should be affected. Hence you can have a hidden door somewhere around, stick some enemies in there, all of whom are in the spawn state and can't hear any noise you make because the secret door prevents the audio propagation, and then when the player triggers it, the door opens up and you're good to go. However, each trigger can only have one function pointing to one object. So what if you need to have two things happen at once? A great example of this is the blue key trap in the toxin refinery. The trap involves walking in to grab the key, only for the lights to dim and a secret door with imps inside to open. Well, the solution is you just place two triggers right next to each other, targeting different objects. There are over 130 of these functions in the game, ranging from opening and closing doors, raising or lowering the floor, locking a door, changing the light levels, teleporting the player, and more. Using this, you can simply set up an environment, and once the walls move and the enemies can see the player or hear a gunshot nearby, we're good to go. But sometimes it leads to some even more creative choices. A really good example of this is in the military base, the secret level in the first episode of Doom, in which the player can trigger a trap by grabbing the rocket launcher sitting atop the pentagram on the ground. When the player crosses over the pentagram, it doesn't change the room the player is in, but rather it removes a small wall that has been protecting a teleporter in a small hidden room locked off at the side. The enemies in the room are already active and moving around, but they need to wander into the teleporter in order for them to appear on the pentagram in front of the player. The trick is that there is a small and largely imperceptible corridor of level that connects the main room with the pentagram to this tiny room on the side. This is used so that any noise that occurs in that room will propagate through to the hidden room and encourage the monsters to head towards the noise, given the sound target will then be assigned. As they move towards the sound target, they will ultimately walk into the teleporter. This sound pipe is actually a fairly common tactic and crops up on other occasions throughout the WAD files of both Doom and Doom 2. But that isn't the only trick that helps make it all come together. The second trick is a little special customization that happens on a per demon basis when the levels in Doom are designed. There is a special ambush flag that can be set on a given monster. MF_ambush sets an additional logic to the previously mentioned C state. If a demon can see the player or hears the gunshot, then they treat that location as a target and move towards it. MF ambush changes this logic so that even if a demon hears a noise that alerts it, it doesn't act on this knowledge until it receives visual confirmation. So the demon is awake and active, but it stays rooted to the spot until it actually sees you. This means that during an encounter, some demons will still be able to catch the player off guard and, as the tag implies, create an ambush. It's a simple yet highly effective trick that, combined with the level tags and sound pipes, can lead to all sorts of interesting combinations. A great example of this is in Containment Area, the second mission of the Shores of Hell. While getting into gunfights often results in kiting the odd zombie man or imp towards you, many of the imps in that level are using the ambush flag, meaning that even when you kill someone right next to them, they still wait until they achieve line of sight before they try to rip your face off. It's crazy to think that Doom is now approaching 30 years old, but it's a game that continues to influence and impact the industry in a myriad of ways, and it keeps getting ported to pretty much every device imaginable. One of the big reasons that Doom is able to appear on everything from PCs to consoles, mobile phones, smartwatches and even ATMs and pianos is because the source code of Doom has been public knowledge now for over 20 years. As we discussed, the game is highly optimised C code, and id Software put the code online in 1997. If you're keen to learn more, check out the links to the source code alongside Fabian Sanglard's Game Engine Black Book on the subject, and the Doom Wiki. All great resources if you're like me and enjoy regurgitating technical facts on the internet so people will say nice things about you. Thus far, it has not worked. Thanks for watching this episode on the AI of Doom. If you've enjoyed this video, you can watch my analysis of the AI of the 2016 reboot of Doom. Plus, over on my game design series Design Dive, we have episodes on Doom 64, Doom 2016, and Doom Eternal. Plus, I want to take a moment to share my appreciation for the soundtrack in this episode, the IDKFA album by Andrew Hulshult, which is just so damn good. That's another link in the video description for you. A special thank you to Brian Omalan, who, like all my other Patreon supporters, gets to watch episodes early, decide future topics, and generally just be awesome as they help me pay the bills. Because electricity is expensive nowadays. Actually, I wonder if we could mine the energy from hell to solve the cost of living crisis. That's not a bad idea, actually. Can't see that going wrong.